Okay, so the next speaker is Andras Némethi. It's going to talk on the reflex module for rank 1 over normal surface singularity.
Actually, this is a continuation of Augustine's talk, and I saw that this is part what remains, so give a precise description of the full sheaves, of simple full sheaves, and characterize exactly the platform. So that is the goal of this talk. So first I need to introduce some notation, very standard notation of normal surface singularities, and then so I tried to work then. So X is a normal surface singularity, and I fix a resolution. At some point, it will be important that it's minimal or minimal good, but in many cases it's not important. And we will use the notation that is the exceptional curve, and we have the irreducible components of the exceptional curve. And I need the two lattices. So one of them is, so if I consider H2 of the resolution, so that is generated by these classes of the exceptional curves. And this has also a negative definite intersection form. So that will be denoted by L. And also using this intersection form, I will have the dual lattice. What I can define also in this way, but I prefer to use as a rational cycle. So I will use the following definition or equivalent definition that is in those rational cycles, such that L is EI, it's integral for any R. I will do also a picture immediately. So then using the intersection form, actually the intersection form is non-degenerate, and we will have the inclusion, and I will use also these portions, and I will denote this by H. So that is the notation. And actually maybe I give for this actually also another interpretation of the dual lattice that can be also identified with the relative cycles and even with the cohomology. And then if I use now the long exact sequence of H2 xz and H2 of the relative dx, and here I write that is the link, actually this is the link. And then we go to the H1 of x tilde z, and after that nothing. What do we see? So that is basically the intersection form. Then we see that is L, that is the dual lattice, and that is H1 of the link. We see that, and also this is free. Actually, it's using the resolution that we have that this is also the same. It's homotopy with the E. So the H1 of E, actually, how many, if we have the exceptional curves, of course, that this is transversal intersection, yes. So we have, we might have the H1 is for each GI, yes, the genus, if the genus is high, we have 2G cycles, and also I have the number of independent cycles in the graph. So that is sum of 2GIs plus the number, I will use in this notation that the number of independent cycles of the graph. So that is free, but this is torsion. So basically what we have here that this is the torsion part of H1 of the link. And so basically this is what I need. And also it's good to know also this number that basically if it's gamma, so it's the link is rational homology sphere if and only if this number is 0. So that means that all the GIs GIs are 0, and gamma is a 3. Some examples I will need also this one. Okay, so this is just the notations, and then let's start the reflexive modules of rank 1. So maybe I will start with the resolution. So the Picard of the resolution. So if we consider the sheaves, the exponential log x sequence associated with this, and then we will have that h1 of x tilde z, h1 of x tilde ox, h1 of x ox. Yes, and here I have h2 of x tilde z. And so what is this? This is exactly the Picard of x tilde. And that is usually, yes, and that is C to the geometric genus. So that is one of the definition of the geometric genus. And that again, it's exactly the same as what I have here. The rank, so that is Z to the, yes, so it's 3, and then, and that is L, and that is the first chain class. So basically that's what we have. And if the geometric genus is non-zero, then of course that we might have here that, yeah, so maybe this divided by that is the Picard 0, usually that's the notation. Those are the line bundles, which are, this is the topological classification, so that is the lattice, that, and the topological classification, and then if topological says 0, then this is the moduli of the analytic classification of the line bundles on the resolution. On the other hand, we have in both objects here and here, we can embed the lattice L. And actually, this is just this embedding, yes. And this is by, if I have a cycle here, then I go to the O of L. Yes, that is very natural. And then I can consider the quotient, so maybe I write again, so I wrote in the strategy that, but anyway, so I will write again. And here I have the Picard, we have here the L, and here is the Chem, here is the L. And then we can consider here the Picard divided by this L, and here also our L, and that is our group H, and that is the Chem. Again, I will use this notation, say C1 bar, that is basically is the Chem class, and this is the same. Here it's absolutely the same. And I want to use this exact, so that is, I think that first was Mumford, and that is the class group, that is the local class group. So that is this is of course that here divided by principal divisor, that is the local divisor, the local class group, and that is actually, this can be identified that with the reflexive modules of rank 1. So that is the object what we have to understand. Yes, so this is exactly the class group of the local singularity. Maybe I put here also the germ. So that is the isomorphic with the reflexive modules of rank 1. And this exact sequence will be important in the next discussion. So what we learn from this? So actually, again, I already Augustine and then here what a lot of talks that if I have an element from this class group, so I will use this notation, but I don't know what's different notations here, that reflexive or yes, but that is reflexive rank 1. Then I can, so for this Augustine and here a lot of talks we already saw also yesterday, we can define full sheaf using the Picard. I will, what is the meaning of full sheaf? So actually here I have, say, the projection, and then also maybe here I use this one. So what was the construction? The construction was that we pull back that M, and then we consider the double dual. And also we can go down, that if I have here shift, then considering and that is M. So that is the bijection between M and the corresponding full shift. What is the meaning of full shift? That M is full, that is globally generated, and also we have that from H 0 x tilde M to the H 0 x tilde minus EM, actually that is on top. Yes, so that is the definition of the full shift, and the point is that I have a unique lift for any element here. I have a unique lift here which is full. Yes, so that is and we want, of course, that here also we have a classification in some sense, but here really we would like to see that if I lift, I have a full shift that is uniquely defined by that property, but that corresponds to some lifting of the chain class. And I would like really to identify that chain class. Yes, so that is now the goal. So maybe I make here a picture that, let's see, if I fix here an H, so let me fix here an H. So that is the chain class, yes, down, yes, at the level of the link, yes, if we go at that level, and then I have here an element M in the class, yes, so maybe I put here an index, usually we put an index H corresponding to those elements which given chain class H. Then I would like to see these elements, so all these lifting, so that is that, say, maybe I just, yes, yeah. I lift this element, so that is, by this diagram, is parameterized by L. So if this is fixed, when we lift, that is exactly a lattice, so that is actually, it's an air torso. So we have a lot of possibilities, a lot of choices, yes, how to lift it, but there is only one, it's a unique one, which is full. And I want to identify that, which one is here. So it's a point of lifting, and I have to identify exactly, yes, C1 of that element, it's important, so that decides, so that is the question that how I lift the chain class from here to here. Yes, that if it's full, if I do this construction, that gives a unique lift. What is that lift? What is the chain class of that lift? And the point is that actually it was yesterday, or 2 days ago, it was mentioned that is not, this choice, this lifting, it depends on the analytic structure and not just this chain class. That's no ask that if this is just, it's a problem of the chain class, but it's not topological. So it might really happen that maybe I make here a different picture that, yeah, so this is what I want now to make here the picture that down, say I have, so that is the Picard 0 down, so I have, say here, yes, I fix an H, that is the Picard 0 torsor, so I have an element here, that is my M, and then above that I have, yes, different lifts of the Picard 0, which are indexed by L, yes, and I have these possible lifts, and then now the question is that where is situated exactly my full shift, and it can happen that, say, this element here lifts here, and all the others lift here. So it's not, it's independent, so it's not a problem of the chain class. It's really of the point on the Picard, and then the position of the Picard 0 or of the moduli of that line bundle. It's not just its chain class. It's not topological. That choice is not topological. I don't know if. So this was just the first introduction. So what I want to do. So the goal is to identify all these chain classes. That's how I live. So basically, to identify here the full sheaves, and the second then, which are simple full shears, and after that to identify all those full shears which are flat. So these three things I want to. Is there any question? Because no, I erase and I start. These leaves actually it was these leaves is it's very interesting. Appears how what is used here in this solution of this problem was used before when I studied basically the Cyber-Witten invariant of the link or the lattice homology of the link. And this was a very natural choice how to lift somehow the chain classes, because that is that if I have a chain class, not chain class, species structure down in the level of the link, then how to lift to the species structure of the resolution. And if the choice was nice, then that had a lot of advantages, and then they also provided some good vanishing theorems. And it's very interesting, exactly the choice is used here. For that, I need to introduce one more. Of course, this is well known, also the Lippmann cone, but let's do it. I will do it fast. I hope that I will have time for all this. So the next step is I want a lift, yes, and so lift. So basically, this is.
So is there an example where you have such a full module and
yes, and immediately in the minimal elliptic case, I will have exactly this.
So you deform it and then it loses the ability to lift?
If you put it different, exactly in the minimal elliptic case, at the end, when I give the complete characterization, I will present also. And already, so that is the minimal elliptic is when really vertical zero, and already that appears. So it's. So it's not just, indeed, it's not just philosophical that might appear. Really, when it can appear, immediately appears. So, yeah, so we have the L, yes. So maybe I give you very fast an example of this. So if I consider the simplest example, so that is the resolution graph, A3, yes, then here the L is generated by E1 and E2, and that I will, this is my lattice, yes. So these are the lattice points. And then what is L2 and what is the dual lattice? So here the determinant is 3, so it's basically it's an extension 1/3, yes. So it's I have the following cycles, 2/3 and 1/3. And if you just please check that that rational cycle intersected with both of them are integral, and then also we have that corresponds basically to this card, that chain class, yes, and we have the other one, the 1/3 and 2/3, that is another rational cycle. The coefficients in this, yes, in this basis, and that corresponds basically to this chain, yes, or that card. And they generate, it turns out that they generate the big lattice, the dual lattice. So the lattice points are this one for the, so these are the dual lattice. So it's, and of course that in the units I have 3 elements, so it's H, and H is this 3. Okay, then let's see what is the Lippmann cone. The Lippmann cone is the entire cycles. So it's saying the rational Lippmann cone is those cycles, those rational cycles such that L with EI is negative for any I. So that usually in algebraic, so that is corresponds to the Neff cone, but here it's negative definite, so it's better to consider this one. And S is the those one which are in L prime, and S is those which are in L. It turns out that S is in the first quadrant, so basically this cone in this case is generated basically by this one, because that is actually the dual, that is EH1 and this is EH1, so that is the dual, that is dual basis, so it's basically generated by those ones. So this is the, that is the Liebman cone, and the elements, the blue elements are of these bigger, say, lattice points, the semigroup, and that is the smaller semigroup. Yeah, very good. And now what I want, that's I made the picture because it's maybe it helps to understand what we want to do. So if I have an element, the element say here in Z3, so that means that I have a class. So basically, what is the class of this? The class of this is exactly L. And what is the class of this? The class of this is exactly this one, this one, this one, yes, this one here. And the class of this is another class. Yes, that is how I lift. How I lift, say, if I fix an H, I want to lift it. Yes, to the dual lattice, and I have all these are possibilities, and I want to make, and the full shift makes a choice. And what is a choice? Well, if I introduce the Liebman cone, you immediately can guess that what is that. So that is a theorem. Theorem that for any H in H, there is a unique element SH in what is this? These are the elements L such that their class is H. So yes, the possible leaves such that SH is in the Liebman cone and SH is minimal. Minimal means that using, yes, maybe I write here that L1 equals Li1 EI is smaller than L2 Li2 EI if Li1 is Li2 for any I. Yes, so that's just usual, so that is smaller than, yeah, so it's clear. So, and that is a theorem or it's a fact, it's not very, that is proved when Art introduced the minimal cycle, then he had something similar. That's, the proof is very similar. Maybe yeah. So for H equals 0, S of H is 0. Maybe a remark here that if I want also, this is that S, yes, S minus 0 also has a minimal element. And that is called the minimal cycle, that is the artist cycle. And yeah, so for example, in this case, the artist cycle is this one, but S0 is this one. So that is only when it's not the same, but if this class, so the minimal element of this class is this one, so here these are exactly the minimal elements. Of course, that this is a very simple case. Usually, to compute SH is very complicated because this cone is somehow, it's small, and the very first lattice points is very, very far, and so that is very, there is an algorithm, we call the generalized Laufer algorithm, which gives this choice or this, but it's even for cyclic quotients or Seifert, so star-shaped graphs, if you want to write down, it's rather technical. Yeah. There is one more step about the lifting. So that is how we lift the chain class. So this was about this step. What is basically it's the most important for us. But there is also another one, which is what is here. So you see, if I have here I explain on this picture, if I have here an L, then for that, actually this is what we did here. That for an L element L, I can write here a line bundle. Yes, very natural. That is L goes to the OL. But what about the rational, yes, chain class? Of course that I have a lot of bundles with the chain class, but is there a very natural lift of that? And what is the meaning of natural? Of course, that's also a question. And the point is that this splits as a group. Yes, it's not totally trivial. But when this has no torsion, so maybe I write also a second theorem that if the link is rational, is a rational homogeneous sphere, so that is not here, so this is actually then free, and then you see this is actually we have to solve something that immediately I write. So for any L from the dual lattice, there is a unique. Actually, I can define, say, I will use exactly the same notation, but be careful. That is no rational cycle, so it's not like the classical case. In the Picard, such that the Chern class of it is what I want, but also has some additional property, and that can be defined in many different ways. But one of them is that it behaves well with the coverings and is an extension of this one, actually. So that if NL, it's an integral cycle, then this should be exactly that one. So somehow that n root, I have a very canonical n root. So that's the point. What is very functorial, very canonical, behaves well with all the constructions. So then I have a good choices. So that is the first HSH, Chern class lift, and after that, maybe this is even more trickier, then it's a line bundle choice. Okay, so that was maybe the very good. So then, and that was, yeah.
In your example, your lifts were generators of the cone. Is that a general feature or is it accidental? The two things are generators of the cone. They generate the cone, the X.
Yeah. So these are the, sorry. Maybe I give you some more details. So, no, that is general fact. So if I define this one, this is the dual one, that is in the, yes, such that by the Kronecker, yes, that behaves in this way, and better to write here negative because of the, yes, then this is actually the basis of the dual, that is, and so that means that, so that means exactly that, yes. So if you have the resolution graph, then this curve, and the other curve, yes. So, and they generate, and this is generated freely by those three stars.
Right, but the lift classes, do they also generate the cone?
These ones?
Yeah.
No, they can be very, very far.
But they could be far on the ray. Are they on the rays of the cone, or are they somewhere in the middle of it? Or so if they all...
No, they are not, they can...
It can be anywhere.
Sorry.
There's not for each ray that is not necessarily...
No, it's, okay. Yes, so it's... So they are not these elements, definitely they are not these elements. At some point, they will be important that SH is exactly of this type, but usually they are combination of these. So let's try to give them answers to the. So let's see first. I won't know really. I have to be fast. So let's see the rational case, rational singularities. So that means that PG equals 0. So in this graph, actually, then the Picard 0 is 0. So we had that L is we had the Picard X tilde, and actually that is an isomorphism now because PG is here 0, and here's the class group, and that is H, and though this is also an isomorphism. So all the reflexive rank 1 modules are classified by H. The question is that how we live. So that is an ambiguity, of L. And then I have to explain that so H, that is corresponds to the reflexive modules of rank 1. And the question is that how to live. what is the choice of the chair class, where that is the chair class here. It's an isomorphism, and I have to identify, so in this case the classification is topological, so I have to identify the chair class. And the fact is, the theorem is, that the M of H, yes, associated with this one, so maybe I write in, actually is OX tilde of minus SH. So that is how yeah. Maybe I put here just to, no. Yeah. So these are the flat bundles, not flat, sorry, full sheaves. Full sheaves corresponds on X tilde, corresponds exactly to OX tilde minus SH, H in H. These are exactly, so you go in the Lippmann cone from each class, so you take the minimal elements, and these are exactly the full sheaves.
What does the W mean? It's W, okay.
Dual, my writing, I'm really sorry. Double. Yeah. And now comes to the next, to the minimal elliptic, yes, case, and that is, already this is nice somehow, that, but here was not really Picard zero, and basically this is a topological decision here because that is combinatorics SH, also the chain class is a combinatoric, so this is a, and then let's see the minimal elliptic. The minimal elliptic PG equals 1, and actually what is the minimal elliptic? Yesterday was already explained, PG 1 and Borenstein. And in that case, we have that is C, we have the Picard 0, Picard, yes, and here it's L, and here we have the class, and that is the H, and the ambiguity is L, and yes. And here H, yes, I see. Sorry. Yes, and here also we can have something. Yes, depending if it's rational homogeneous or not. H1. Yes. And so again, what is happening that here I have an element and I want to lift. Yes. And we have to make the distinction between H0 or H not 0. If H0, then I have here corresponding to H0, we have here the class, yes, what is exactly the classified by the Picard 0. Then I will use this notation, yes, somehow, yes, and then we have to lift. Yes, again the ambiguity is the lattice L. And we have here two cases that if this is 0 here, so the 0 element, if M is 0, then the lift, of course, should be OX tilde, should be 0. So then here we have, yes, exactly the elements, that is the 0, and that is, it's an L torsor. Then this element lifts here to the level 0. And all the other elements, if M is in the Picard, yes, minus the origin, yeah, then the chain class should be an integral, but then the corresponding lift, the full shifts is OX tilde minus the minimal cycle of RT. So exactly this is the case what you asked, that here this element goes to the 0, but all the other ones go to the minus Z min. And this is a whole. So that is, and if H is not 0, then somehow that is a little bit, yes, special, say this M equals 0 here, but still it's interesting that you have this choice. here it's very similar in that one, that we have that for any h that we have the lift is ox tilde, so the full, these are the minus sh. Again, that is in the sense of the lift. You leave the chain class, that is a rational cycle, and then you make the choice, yes, of the corresponding line bundle. So here the full shifts are the following type. So we consider O of x tilde minus z. So the Picard, maybe I do in this way. The Picard with chain class minus z mean. But here exactly we delete the corresponding, this corresponding to the O x tilde minus z mean. That it would be the lift of this, the canonical lift. These are all the, say, the in the moduli, but yes, in the very same chain class, but the moduli, that is a C, yes, C star, and here it's we delete this. Corresponding to this point, we put back OX tilde, and after that, we make union over order H non-zero, the Picard minus SH. So these are lifted corresponding to SH, and uniformly no trick like this. But at the level 0, H equals 0, there is this, we have to be careful.
Can you show us in the picture there what is minus SH?
So SH, you see, these are the somehow, yeah. Why is the minus?
What is it? I don't know if you told us what the construction of this is. You just told us.
It was the second lift. So that is a rational cycle in a, yeah. So yeah, so this for any rational cycle, there's a unique lift line bundle here with that chain class. So this is for L is clear that L you go to the OL value, and that is a finite index, and the here yes, and then you lift. But actually here, what is important that is uniform. So you don't here. What is important just the chain class basically. But yes, when is this is rational homogeneous sphere, then this can be uniform. It's you see it's you have a rational cycle, yes, and you go to the universal abelian covering. If you lift back this, you pull back this, that is exactly an H covering. So that means that if you pull back that, or your rational cycle, that became an integral cycle upstairs. And then take OR there, and you push down. And that will be a eigenspace decomposition, and you take the right one.
So in the smooth projective case, if you have a smooth projective variety and a bunch of hypersurfaces, and then you consider a rational cycle and a line bundle such that the Chern class agrees or with the cycle, then that's a bijective correspondence with unitary local systems on the complex, Francois. Is there some topological interpretation here?
Yeah, here it's yes, something similar, but here the branch, so it's on in the origin, so it's not really a branch. It's, the branch loci is smaller. So yeah, but basically we have a system. You have a you can also make interpretation that way, because yes, corresponding to discovery, yes, that gives a representation. Yes.
I'm opening over the link.
So this is at this level, yes, this is at this level, the resolution. You do first this one, that is an SH, so basically that's what, to an element here, we associate here a line bundle. But using some universal, yes, this SH. So now the next step would be the simple, yes, the simple full, and after that the flat, simple full, and after that the flat. Maybe I finish fast the simple case, and then because it's more interesting the flat, the classification of flat bundles. So the simple was it was Wunram. Or I don't know if anyway. So it's so M full sheaf is simple if H1 of X tilde, we have one more additional homological condition. So what is here? What
Homological is special. It's special.
special, not simple. Sorry, I special. Yes, and common. Okay, I'm sorry. So what I thought simple is not simple. It's special. So yeah, it's special. So just one remark here. So yeah, homology. Okay, but so also this SH was very good because of it is compatible with a lot of vanishing theorems. Some of that minimality, and but also here we see something similar, that you see that the full sheaf was that it should be generated by global section. So that means that H0 is big. H0 is big, H1 is small. But here that's exactly the opposite tells me, that here it's H1 of the dual, H1 of the dual is small, so then H1 of the M should be big. But the other one tells me exactly the opposite. So somehow the two conditions that this condition and that is globally generated, they from two different directions pushes in opposite. Yes, so it's between them, there should be something or nothing, or maybe it's very special one should. That's it special, yes. Because the two conditions are very contradictory, or very in the they give very opposite, say, directions for the existence of the sheaf. And maybe, so I recall the theorem of Unram, which tells me in the rational case, rational singularity case, actually the special indecomposable, non-trivial, full sheaves, reflexive modules, or full sheaves, that is the same, but that corresponds to exactly to the EIs. So in the, maybe I should explain, or actually was already told, that in the case of the quotient singularity theory, the beginning, when the Macaulay correspondence appeared, that was exactly the EIs, the representations, and also the reflexive modules. That is one-to-one correspondence, and that corresponds exactly to the chain class. That exactly that cut. If I have a module, then where is the chain class? That exactly, yes, that operates on the EI, so where it's exactly intersects the EI, and that was the Verdier point of view, and that was the one-to-one correspondence. But if you go to more general situation, of course, that we cannot expect that the exceptional in the minimal resolution, that you have a correspondence of between the EIs and then the representations of the full sheaves. But still, for the special case, Wunram proved this. And again, it's given by the chain class, and even more the rank of M here corresponds exactly to the coefficient of Z mean of the corresponding I. So if this has Chern class, some Chern class which is a cut of the EI, yes, then the rank, yes, its rank of M corresponds to the coefficient of the Artin cycle in I. So in our case, of course, that if we study the rank M, rank 1 reflexive modules, then we might go also in this correspondence, and then if we put everything together, actually we have an independent proof of this, but yeah, everything is joint work with Augustine, sorry, at the very beginning I didn't. So that is our paper. Then we have that, so that is the theorem, that L OX minus SH, yes, so these are all the full sheaves, yes. In the rational case, that is, and this is special, if and only if we have the following, either this SH, yes, intersected is the minimal cycle, Artin cycle equals 1, or this SH equals, so that is an EV star, and that MV, so that, okay, MI, MI, and MI equals 1, that is MI. So there is a combinatorial way somehow to check that which reflexive modules are exactly the special ones, and that is in the language of SH and the Artin cycle, one can decide. So basically that is the point, that the corresponding Chern class should be, yes, I should have a cut there, also by this one, but that should be exactly the SH. So in that is exactly the case what you asked me, that SH, then it's a very natural choice. It's exactly the dual element in that case. Okay, so maybe it's more, I don't know if it's any question.
What is the assumption of the theory?
So this is for rational singularities. Then this is the yes, so now we go to the flat bundles, and we have a complete classification of which reflexive modules of rank 1 are flat, and we give also, in this case, in the rank 1 case, answer to the rank S, and this conjectures about that, for example, for a cusp case, that any reflexive module is flat. That the conjecture in the rank 1 case we can prove even log canonical, but we give very precise answer characterization. So what is now the picture? So the flat rank 1. So what is the meaning of that? That we have, yes, we have the link. That is the link. What was also in the previous notation was the boundary of the, yes, of the resolution, or the boundary of X, if you want. Yes, if you cut is the sphere, and we have to classify H1, yes, of the sigma of C star. So the rank 1, yes, flat rank 1. So we have the representations, and we have to classify exactly this one. And we have the following diagram, so that was already considered. The class, yes, so that is the order, yes, the reflexive modules. This goes to H. And if I write, so that was associated with the sheaf O star. And then after that, I cut with L, yes. But I can consider also this C, and that will be the point, that to compare these two diagrams, so the associated homology long sequence. So if I consider that one, Then again, we will have here h1 of x. So right now I have here c, yes, and here we will have the h1 of yes, and here again I have h. And that is the very same one. And there are some natural, yes, sorry, I have to put here sigma. And also here I have to put sigma, but they are the same. Yes, I already I use it.
Sigma is what?
Sigma is the link. Sigma is the link. And then you have here a natural map. Actually, you have here that is C to the PG. And you have here a natural map. Actually, by using that, this is, you make isomorphism. Actually, this is the natural isomorphism here, that to XC. But you prove that that is an isomorphism. But, and then know this C has a map here. Yes, that these are the constant functions, and that gives a map here. And it's much harder to, not harder, but the point is that you can define also here a map. Actually, we know that what is that map. That map is that if I have a representation, then we consider the flat bundle associated with it, or yes, and after that, yes, M rho is O x tilde or minus 0, and that is our M. Yes? So we have associated with the representation, we know that we have a module, and the point is that that map fits with this diagram. That is one should check that. And now, if we have this, then it's very natural everything. No, we have all the answers, because that is an isomorphism, So basically, that this is subjective or not, it depends on this map. And that is exactly what is considered in Hodgkin, Dubois, of singularities, yes, or Dubois, yes. But H1, yes. So actually, I can replace this one by H1 of XC. So actually, this map compared with this one, so this map, that is basically the Hodge decomposition of, yes, in some sense, but it's no, we are in the local case. Yes, decides that this is subjective or not. So what we have, that is the theorem, that H1 of X, H1 of sigma C star, so these are the flat bundles, yes. We go to the class group that is onto if and only if this H1 of sigma H1 of X tilde C goes to the H1 of XOX is onto. And even more, the kernel of this map, so that means what? That means that to decide if two representations provide the very same bundle, yes, that is the same, this kernel, then the kernel of H1X tilde C goes to the H1 of X tilde or X tilde. That is the CPG, and that is the C on the sum of 2G of EIs plus the cycle in gamma, independent cycle in gamma. So we have this map decides about everything. If that is subjective or not, or if more representations provide the same reflexive bundle or not. And now if I have some time, I can give you some examples, the rational, cusp, and then some singularities, just exemplifying. 5 minutes, then each minute 1 case, that's it. Yeah, I have, I think, 5 cases, but I don't have to go through. So let's see the rational case. The rational case here it's 0, PG is 0, and it's a rational homosphere, so this is also 0. This is 0, 0. So then H1 X tilde C equals H1 of X tilde or X tilde is 0. So that means that this is an isomorphism. H1 sigma C star goes to H1, the class group, this is an isomorphism, and actually even we know that that is equals H. And that is an isomorphism, and it's isomorphic also is H. Yes, so in that, but it's very interesting that even for rational case, I don't know, it was no. Really. And so let's see the minimal elliptic. If we consider a minimal elliptic case, and or even yeah, so just rational homology sphere, rational homology sphere. So that you see that is the topology basically. This is the topology of the link, and this is the H1 of the link, and this is that is the PG. That is a lot of analytic structure here, yes. But if it's rational homology sphere, then H1 of X here, the C is 0. But if it's say be not rational, then H1 of X or X tilde is CPG is non-zero. So that means that this is 0, this is non-zero, that exactly that ambiguity survives also here. So I have a lot of, bundles which are not flat. That was first constructed by Augustine and collaborators. So it's then we have, and on the other hand, this is injective, so the flat ones are represented by one representation. So that applies also for all minimality. But let's see if I consider the cusp. In the case of cusp, so that is the resolution graph. That in this case, that is a C. So we have H1 of sigma C or X tilde is a C. Yes, and also H1 of X tilde OX, that is also C. And that is an isomorphism. So yes, and then C goes, and that map actually is not just that C is isomorphic with C, but that map is an isomorphism. So that means that this is also an isomorphism. So then we have that H1 of X, sigma C star to the class group actually is an isomorphism. So that means that any bundle actually is flat. That was a Banker's conjecture, and also it's uniquely represented. There's only one representation. Yes, and also this applies also for the low canonical. That was also another conjecture, the extension of this, but that is also true. Why is that any bundle, any reflexive is flat? Why? Because low canonical is either rational or cusp or minimal elliptic, or not minimal, simple elliptic. That also simple elliptic here we can, maybe I do also simple elliptic immediately. But that was already known by Kant that any it's flat, any representation is flat, but in rational and cusp from this discussion. Maybe I write also a simple elliptic somewhere because that gives that is known when it's not injective. So what is the meaning of simple elliptic? The simple elliptic means then the resolution graph is something like this, minus B. And in that case, actually it's E, it's an elliptic curve. So H1 of X tilde C is a C squared, but it's elliptic singularity, so X tilde is a C. So we have that C squared and C, so that is our map here. So that is surjective. So that means that this map H1 of sigma C star to the class group is surjective. So all of them are flat, but the bundles somehow are represented by many different representations. So it's not unique, the choice of the representation. Yesterday you asked some similar question at some point, that if it's unique representation. So in the examples But this theorem basically clarifies that also the subjectivity is also the objectivity.